I'm so honored to be with you to communicate academic questions and ideas. The title of my academic presentation is A Portable Brick Computer Interface Using Microdisplay for Future Mobile Communication System. I shall take only 20 minutes of your time. First of all, I wanna introduce the background of our studies. Then I will show the hardware of our BCI system. Thirdly, the software environment of the system will be shown. Some key performance we have got is shown in the last part. Firstly, some background and concepts of this study are introduced. As shown in the first picture, the communication between devices have been effectively enhanced by the latest mobile communication technologies, such as enhanced mobile broadband, massive machine-type communication, and ultra-reliable low-latency communications. However, the conventional keyboard and mouse communications are still used in human-machine communication between users and devices. In the future, it is possible to make devices read our brains so as to achieve more efficient human-computer interaction. If we could implement a communication system like the one on the right, we could allow our brains to communicate directly with machines. At present, the above-mentioned ideas are gradually being realized by BCI technology. There are four types of BCIs: P300 BCIs, motor imagery BCIs, slow cortical potential BCIs, steady-state visual invoked potential BCIs. BCIs can liberate hands so that to replace keyboard and mouse. However, BCIs are still expensive and the devices are still huge. Thus, the application of BCIs are still limited. When the subjects are gazing at flicker stimulus at a specific frequency, the external cortex of the brain will produce fundamental responses and harmonic waves, such as the left picture shows. The SSVEP signals usually have high SNR and observable features. This kind of EEG signals are used in a lot of BCI demos. But the SSVP BCIs have poor portability and will cause visual fatigue. In this paper, an intelligent crawler robot control system is designed for cleaning the walls, which is considered as one of the smart home appliances. The user can control the robot to move in 4 directions by gazing at 4 different frequency stimuli on the computer display. A UAV control system is implemented using SSVP paradigm. Seven commonly used commands of UAV are encoded by seven stimuli with different frequencies. User needs to conduct data training before using the system to ensure the decoding performance of the UAV control system. The previous demos used computer monitors to present stimuli. Such stimuli presentation scheme is obviously not portable for users. This study used a portable AI glasses to present stimuli. All data transmission in the control system adapts wireless transmission. This study shows that when stimuli size are reduced, as long as the stimuli are kept in the visual field, SSVP responses can still be stimulated in the brain. The same team also published another paper that SSVP BCIs can be used to control manufacturing equipment. This study also demonstrated that under normal indoor lighting conditions, the stimuli shown in the AR glasses can still stimulate the brain to produce EEG signal with obvious features. In order to minimize the size of the equipment used to display SSVP stimuli, a monocular AR display is used to present the stimuli. The left picture shows the appearance of the subject after wearing the devices. Secondly, the hardware platform selected for this study is introduced. Three types of hardware are involved. We chose a monocular microdisplay to present external stimuli, collect brain responses to stimuli through EEG electrode caps, using a quadcopter to show the decoding results. Five control commands of UAV are encoded by five visual stimuli, which have different frequencies. To ensure the detectable frequency features can be collected, EEG signals were collected at 9 cents on the surface of scalps that are highly correlated with vision. By gazing at visual stimuli in the microdisplay, the user generates EEG signals that are processed and decoded by the computer and set commands to the UAV. This allowed the UAV to perform control commands corresponding to the flicker stimuli. The method of generating stimulus and decoding EEG signals will be introduced in the following part. The joint frequency phase modulation method is used to present visual flicker stimuli on the microdisplay. 5 rounded stimuli are used to encode 5 flight commands of the aircraft. The radius of each flicker stimuli is 280 pixels. These 5 different stimuli correspond to 5 control commands for the UAV. In applications such as UAV control, we usually hope that any user can directly control the UAV after vary the devices. Therefore, data training will reduce the user experience. UAV need to fly in the open air, which means that the light can interfere with visual stimuli. Thus, the decoding algorithm is required to have nice environmental robustness. In addition, due to the need to process the EEG signal in real time, the algorithm with high complexity is not suitable for such online system. CCA algorithm for decoding EEG signals has the above characteristics, and it also can detect EEG signals asynchronously. CCA algorithm is a special filter method. The EEG signals collected for each channel usually don't have obvious features. The special filter gives different weight coefficients to different channels and then superimposes the EEG signals of these channels, so as to obtain a group of signals with obvious features. The right picture is a schematic of the special filter method. The signals shown in the picture is actually collected EEG signals after superposition. It can be seen that this method can effectively improve the SNR. The CCA detection algorithm based on sine and cosine reference signal is used in this study. By solving the problem of the maximum correlation between the Formula 1 and the collected EEG signals, the EEG signals in multiple electrode channels can be superimposed to reduce the noise. Through Formula 3, the frequency of flicker stimulus that the user is gazing at can be obtained. In order to filter out the EEG signals when the user is not gazing at the flicker stimuli, the UAV will execute the corresponding command when the maximum correlation coefficient between the EEG signals and the reference signals is satisfied with Formula 4. Finally, the performance of the UAV control system will be demonstrated. The accuracy of four subjects at different EEG sampling time and different threshold gamma is shown here. The results in table indicate that the threshold value and the time window of collected EEG signals need to be adjusted according to the EEG signal quality of different users, so as to ensure a better user experience. The results in this study also show that the users can control the aircraft stably in outdoors with complex light interface while using the proposed scheme. We would like to thank all the participants who helped us with our experiment. That's all. Thanks for your attention. The video of the brain-controlled UAV test flight is at the end of this report.